Welcome back to Chem 4300. In this video, we're going to look at Chapter 20 on identical particles and quantum mechanics. Now, back in your high school days of learning chemistry, one thing that you learned about was the Pauli exclusion principle, named after Wolfgang Pauli. And you learned to use that when you were building the electron configurations of multi-electron atoms. You know that no two electrons could be in the same orbital with the same n, l, m sub l, and m sub s values. They had to have different m sub s values to be in that one particular orbital. So that Pauli exclusion principle was something that you applied over and over in the freshman chemistry and so on, but you probably never had an opportunity to learn why that came about. Why was that rule there in the first place? That's what we're going to look at in this chapter. One of the things we'll learn in this chapter. So let's imagine this basic scenario, whether this is a classical physics problem at the moment. Let's imagine you have two bowling balls that are being fired out of bowling ball guns, and as they get fired out of these bowling ball guns, they have a detector on the other side over here, and what you want to know is which one of these two bowling balls hits the detector and which one goes out and doesn't hit the detector. Now, you could easily watch this with your eyes, assuming they're not fired with too high of a velocity, and you can see as these bowling balls come together that maybe this one collides with this one ends up bouncing out this way, while this one ends up bouncing down here into the detector, and you see that that one ended up there and that one flew out over here. Or you can imagine another scenario where maybe they miss each other and this one just goes right through and hits the detector and that one passes through over there. But you can watch what happens as they pass in this collision region, and they're both in this collision region, and you can still watch what happens and see which one goes to the detector and which one doesn't. Okay? Now, it's not a big issue if you're watching bowling balls, but what if you were watching electrons and you had an electron gun here, an electron gun here, and you fired single electrons, on the button, you push, that fires both of them at the same time with the speed so that they're both in this collision region at the same time. Can you determine which electron hit the detector? Well, the problem is that the uncertainty principle says that we can only know the momentum and position to a certain precision, right? So delta x, delta p has to be greater than or equal to h bar. And if we fired these guys at a specific time at a specific speed, then if they're in this region, if we knew they were in this region, we wouldn't know with precision their momentum. So somehow, once they get into this collision region, the uncertainty principle prevents us from knowing exactly their trajectories. We can't know their momentum and position and follow them with the precision that we need to figure out if there was any collision or not. If there was no collision, then this one goes through. If there was a collision, then maybe this one ended up at the detector. So we have this problem that the uncertainty principle prevents us from knowing what happens when these two electrons get close enough to each other and then they separate again. We can't know which one was which. They're perfectly indistinguishable, and the uncertainty principle doesn't allow us to keep track of what happened when they got into this region of proximity to each other. So this is where we are. We have to preserve indistinguishability of these two electrons in order to avoid breaking the uncertainty principle. Okay? We cannot know which one is which. When their wave functions overlap strongly in this region, essentially we can't tell them apart. So any quantum mechanical treatment we put together has to account for this indistinguishability. So when we write down the Hamiltonian for those two electrons, say, we would put a label on these coordinates. So P1, P2, R1, R2. But if they're really indistinguishable, then the results that we get with this Hamiltonian should not matter on how we labeled these quantities. So I can make this P2, P1, R2, R1, and I should have exactly the same results in my quantum mechanical calculations. So these two Hamiltonians have to be invariant to particle exchange. If it wasn't true, then we would violate the uncertainty principle, and that wouldn't be allowed, right? So if we operate this Hamiltonian on the wave function for the two particles, the two electrons, we'll get back the energy eigenvalue times the original wave function. But if we exchange the particles, exchange the labels, then this Hamiltonian on this wave function will give me back exactly the same energy eigenvalue. So this Hamiltonian and this Hamiltonian are the same Hamiltonian. This energy and this energy are the same energy. But this wave function and this wave function are not necessarily the same. And we'll talk about that in a second here. One thing I want to mention is that I'm using this notation of x1 vector, x2 vector to describe the position of these electrons. And remember that for the electron, we have to include its spin state to describe its total state, right? So the electron is in some position x, y, z in space, and it has a spin state, say, up or down, right? I could use spherical coordinates, or I can use Cartesian coordinates. It doesn't really matter, but I do need to include the spin state to fully specify where the electron is and what its orientation is for its quantum number associated with the spin. So this x then is going to be four coordinates, four components when I describe the coordinate vector. All right, so let's get back to what we were talking about here, is that we have then Hamiltonians that have to be equal to each other, energy eigenvalues that have to be equal, but it doesn't really imply that those wave functions are exactly the same. So this wave function squared is the probability density for particle 1 to be at x1 when particle 2 is at x2. Whereas when I swap the labels, this is the probability for particle 1 to be at x2 when particle 2 is at x1. And those aren't necessarily the same. But we do require that the probability density not depend on how we label the particles. So what that means then is that if this Hamiltonian with 1, 2 labeling operates on this wave function with 1, 2, it should give me the same result of this Hamiltonian with 2, 1 labeling acting on the wave function with 1, 2, and give me that energy eigenvalue back. Okay? And likewise, if I have the Hamiltonian labeled 1, 2 acting on the wave function with the coordinates 2, 1, then it has to give me the same result of the Hamiltonian 2, 1 acting on the wave function with the labels 2, 1 to give me back the same energy times the wave function. Okay, so you see the constraints that we have to have here. So these wave functions, they have the same energy eigenvalue associated with them, but they're not necessarily the same. So any linear combination, because they have the same energy eigenvalue, they're degenerate, any linear combination of them will also be an energy eigenstate of H. So what we need to find is there's some linear combination of these two wave functions that will preserve the indistinguishability. And any linear combination will be an eigenvalue of our Hamiltonian with the same eigenvalue E. So we're going to introduce a new operator that we call the particle exchange operator. And what it's going to do when it operates on the wave function, it's going to convert it into the wave function where we've swapped the particles. So P on the wave function with x1, x2 gives me the wave function back with x2, x1, and P on that wave function with x2, x1 gives me back the wave function with x1, x2. Okay? So these guys are different, right? When this operates on the wave function, I don't get back the same wave function. Similarly here, I don't get back the same wave function. So obviously those are not eigenstates of this particle exchange operator. If I look at the commutator of the particle exchange operator with the Hamiltonian, and I remember how we evaluate the commutators operated on the wave function, if you expand all of this out, you can see pH times the wave function minus HP times the wave function. I can evaluate H times the wave function is just E times the wave function. Here, I can evaluate this permutator, this particle exchange operator here and then evaluate the Hamiltonian on this. And what I get back is E times psi of x2, x1 minus E times psi of x2, x1. I get back 0. So just look through that carefully. But you see that the particle exchange operator with the Hamiltonian is always equal to 0. And if it's equal to 0, that means that H and P have the same eigenstates. All right? So what are the eigenstates of P that are also the eigenstates of H that will allow us to solve this problem? Since these guys are not the eigenstates of P, we find that there must be some linear combination of these which will be eigenstates of P and also eigenstates of H. And that will preserve our indistinguishability. So we can find those eigenvalues of P if we know that P operates on a wave function and we get back the wave function times itself. And this is the unknown wave function that we're going to try to work out. Then we know that P applied twice has to get you back to 1, right? So it becomes the 1 operator, identity operator. So P squared, P applied twice gets you back to the same function. So I can take that operation and I can do it in steps. So the first step gives me lambda times the wave function. The second step gives me lambda again times the wave function. So now we see that we have and that lambda squared has to be equal to 1. So that now we have a differential equation in the sense that we can solve and see that our eigenvalues are just plus or minus 1 for this exchange operator. So we have 2 eigenvalues with 2 possible linear combinations. Here's one linear combination, and here's the other linear combination. This has a exchange operator eigenvalue of plus 1. This has a value of minus 1. Both of these are eigenstates of the energy operator. So this will be an eigenstate of the energy operator, and so will this one. We call this combination where we add them together and normalize with 1 over the square root of 2, the symmetric combination. And we call this combination where we take the difference and normalize it, the antisymmetric combination. And these 2 combinations will allow the particles to be indistinguishable if they have this wave function or that wave function. So, and you can easily check that if I apply the exchange operator on S, I get back S. So it's an eigenfunction of the exchange operator. If I apply the exchange operator on A, I get back minus A. So it's also an eigenvalue. Okay? So you may wonder, there is this negative sign here. Does that make the particles distinguishable? Not really, because remember that it's the wave function squared. It gives you a probability, and that negative sign gets lost when you square it to get the probability. So in the end, probabilities are all you can measure, so we've lost the ability to distinguish them just on the basis of that negative sign there. If you did the same procedure for 3 identical particles, I won't get into it, but you can get this combination of your exchanged wave functions to get a version that's the symmetric version. And for the antisymmetric version, this is what you have. And this would be invariant. These would not reveal which particle is which, and it would allow us to preserve the indistinguishability. All right? So it turns out then that there are only 2 types of functions, wave functions we can have, symmetric and antisymmetric with respect to exchange of the particles. And the Schrodinger equation, as we've been working with it so far, doesn't allow symmetric functions to ever evolve into an antisymmetric function or vice versa. So particles can never change their symmetric or antisymmetric behavior under exchange. So when we find particles that have half-integer spins, so s equals half, 3 halves, 5 halves, these are always found to have antisymmetric wave functions with respect to particle exchange. So all of these particles are classified as a group of particles called fermions. They are antisymmetric with respect to particle exchange. Particles with s equals 0, 1, 2, all the integer spins, will always have a symmetric wave function with respect to particle exchange. these particles are classified as bosons. So we have two types of particles depending upon their behavior with respect to particle exchange. If they're antisymmetric particles, they're fermions. If they're symmetric particles or particles whose wave function is symmetric, they're bosons. Okay. We're not going to learn why, but you have to get into a much more advanced quantum class to sort of understand why they have this kind of behavior. But we're going to sort of leave this as a postulate for quantum at this point. Now, when you have composite particles, like a nucleus, maybe a nucleus has protons and neutrons in it, or an atom has neutrons, protons, and electrons, the composite particle will be either a fermion or boson depending on what its constituent particles are. So if you have an even number of fermions and any number of bosons, then it will always be a boson. It's the even number of fermions here that really makes the difference. If you have an odd number of fermions and any number of bosons, then you will always have a fermion present. So identical hydrogen atoms will be bosons. Hydrogen atoms have an electron and a proton at the nucleus, and they will always be, that's two fermions, the electron and the proton, so that means that that will always be a boson. Now again, they all have to be in the exact same energy eigenstate. So if they were in different energy eigenstates, then you would be able to distinguish them. So if you had them all in the ground state, you would not be able to distinguish one from the other. Let's take an example here. Let's say we have lithium isotopes 7 and 6, which have different abundances here. Do we classify the lithium-7 isotopes as fermions or bosons? So for lithium nuclei, they have 3 protons, and they're all spin half particles. So they all have an odd number of protons. The lithium-7 has an additional 4 neutrons. Remember, neutrons are also spin half. So that means that we have a total in lithium-7 of 7 spin half particles. So that tells us that lithium nucleus is a fermion. The lithium-6 nucleus, it has additionally 3 protons, but now it has 3 neutrons in a lithium-6 nucleus. So that's a total of 6 spin half particles. So lithium-6 nucleus is classified as a boson. So I'll leave this for you to work out. These are the various isotopes you can calculate, or look up what the number of neutrons and protons are in the nucleus, and then work out whether those nuclei are bosons or fermions. Now, the next thing I want to talk about is something called a Fermi hole, which sort of arises as a consequence of this behavior. If you remember that the antisymmetric wave functions have this difference here. So if two fermions, two identical particles that are fermions, approach each other and they have not only x, y, and z, but spin state, so the 4 components of the coordinate come together and they actually show up in the same point in space with the same spin state, then what happens is that x1 and x2 become equal to each other. And because of that negative sign here, that makes this function and this function entirely identical, and it goes to 0. They completely cancel each other out. And since we know, okay, again, that means that it's spin and position, right? And since this guy cancel each other out and we get 0, that means the square of the wave function, which is the probability, is also 0, right? So that means that if we're looking at those two particles coming together, if they go to the same point in space, then you see that there's effectively a node, in a sense. Where we talk about wave functions having a node where the probability goes to 0, well, the probability will go to 0 whenever these two particles show up at the same point in space with exactly the same spin state. Okay? So that is what's called a Fermi hole. So if I have a fermion here and another fermion, identical fermion comes nearby, then there is really no place for the other fermion to get into that same location in space. The wave function will go to 0. So they'll avoid each other in a sense. They won't come together, because if they came together, then the probability goes to 0, and that's just not likely to happen. So this is sometimes called an exchange force, but technically it's not really a force. It's just the fact that the probability goes to 0. okay? And it's a property only of the antisymmetric wave functions. The bosons don't do this. It's only the fermions that do this. And so the region around an electron that is excluded to the other regions of the same spin is something that's called a Fermi hole. So now we're going to look at the indistinguishability of non-interacting identical particles. Now, when we have two particles that, or multiple particles that aren't interacting, we can always write the Hamiltonian for the total system of particles as just the sum of individual Hamiltonians governing each of the individual particles. Now, these Hamiltonians for identical particles will have to be identical to each other, right? They'll be indistinguishable for particle exchange. And when we have this kind of situation, one of the things we can do is we can write the total wave function is simply the product of the individual wave functions for each of the particles. But now, again, we have to preserve indistinguishability, so we won't be able to use wave functions that look like this with the labeling scheme like that. We're going to have to build, if we're talking about electrons, antisymmetric combinations to do this. But this will be the starting point for the multi-electron atoms and molecules that we'll be talking about later in the class. Now, what you remember from your high school chemistry is that the Pauli exclusion principle told you that you weren't allowed to take an electron and put it in an orbital with the exact same n, l, m sub l, and m sub s values. They had to have different values of those quantum numbers. So you would change the m sub s state. If you wanted to put it in exactly the same orbital with n, l, and m sub l, you had to change the m sub s states to get them into that orbital. And now you see how that might make sense, because what we have is for that orbital, there's some coordinates in space where that orbital would be, and that coordinate involves x, y, z, and some spin state. And if you placed the electron in the orbital, which occupies some region of space with a particular spin state, and you try to put another electron into that same orbital, which occupies the same region of space with the same spin state, then you can see that the shape of that wave function, the shape of that orbital, with the same spin state, so all four quantities in here, in a sense, then this function and this function would be exactly equal to each other. So if x1 and x2 are equal to each other, then the probability will go to 0, because the antisymmetric combination that you have to create in order to keep those two electrons indistinguishable will mean that the probability of that happening is absolutely 0. So that's why we had to invoke the Pauli exclusion principle, because the probability of that happening would go to 0 if they had exactly the same state, because they're fermions. Okay? So this is what's called the Pauli exclusion principle. It's a stronger constraint, because what it means is that because these wave functions can be written as separate for each electron because they're non-interacting, then that means that the actual functional form, if this is a 1s electron function, and this is a 1s electron function, and the spin states are the same, then you can see mathematically this whole thing will have to go to 0, right? And that's a sort of stronger constraint for non-interacting fermions. Now, there is a really simple way that you can construct an antisymmetric total wave function from all these non-interacting electrons wave function products, and that is to evaluate something called a Slater determinant. So if you have n identical and non-interacting fermions, so that you know that you can write your wave function as this product of individual wave functions, and you know that they're going to occupy n quantum states, so capital N for the number of fermions and lowercase n for the number of quantum states, then you can construct a determinant where the number of quantum states is all going along the horizontal here, and the number of particles, or the non-interacting particles, is going down here. So this goes from 1 to capital N, and this goes from A to lowercase n. If you place all of those states here, so this is electron 1 in state A, in state B, state C, all the way up to state N, and this is electron 2 in state A, state B, so on, up to state N, and so on here, then putting all of those functions in here And evaluating that determinant gives you guaranteed an anti-symmetric wave function that obeys the Pauli exclusion principle and the uncertainty principle that we have to worry about, not violating, right? So if I take a case like this where I have a 1s, 2s, 2 electrons in the 1s, 1 electron in the 2s, then 1 electron can be put in the 1s in the up state, 1s in the down state, and the 2s in the up state. That's the first electron. The second electron could go in the 1s in the up state, the 1s in the down state, and then the 2s in the up state, and so on. We can put the third electron like this. So those 9 ways, those 9 individual wave functions with the different particles assigned, evaluated in that determinant, here's expanding it out one step, and then the final step, gives me this whole function here, which probably is more compactly written here, of course, but this whole function here, which is an anti-symmetric combination for those non-interacting particle wave functions. So again, we're going to be talking about non-interacting particles as a starting approximation, and we're simply, because they're non-interacting, going to multiply the wave functions together. But that's not going to be valid if we don't want to violate the uncertainty principle. So we're going to use these Slater determinants so that we can do that multiplication this way in order to get an anti-symmetric wave function that allows us to preserve the indistinguishability of the particles. Okay. So these things will enforce your anti-symmetric properties that you need, and you can even see, for example, that if you try to place 3 identical electrons in the 1s orbital, for example, I'm going to put, here's here's the first electron, I put it into the 1s orbital, and I'm going to put these guys here. So I have this case and this case, they have the same numbers, but if you evaluate this determinant, this whole thing will go to 0. So this determinant actually will check if you try to put identical electrons, 3 identical electrons into the 1s orbital, up, down, and then up again, it's not going to work. And it's going to give you a determinant of 0. So this is very useful approach when you're trying to enforce these rules. So that's it for this chapter, and now we're really ready to start talking about multi-electron atoms or molecules.